Hello and welcome to this quick video, well I say quick, I have no idea how long this is going to be, in which I'm going to prove to you the circle theorems, just in case you're asked to prove these in your exam and you want a bit of an idea of what to do. So we're going to start with the cyclic quadrilateral. Okay, 1, 2, 3, 4, so I'm just going to draw a cyclic quadrilateral. And I need to prove that the opposite corners add up to 180. So what I'm going to do is I'm going to cut my picture into 2 triangles, like that. And I'm going to say, well, let's call this one A and this one B. And let's call that one C and that one D. And I need to show that A plus B plus C plus D equals 180. Okay, now I know from the theorem that says angles subtended from the same arc are equal, or angles in the same segment are equal. So if I look at this chord here, I can see that D is going to be the same as D here, because they're angles in the same segment. And if I turn it around and look at this one instead, look at this chord, I can see that if that's B there, then this one here is going to be B as well. And if I turn it around this way, I can see that looking at this chord, if that's A, then that one there has to be A too. And if I turn it around this way, I can see that using this chord, if that's C, then that there is going to be C. Okay, and I can write all of those down, by saying angles in the same segment are equal, therefore this one equals this one, that one equals that one, that one equals that one, that one equals that one. Then finally I can say, well, this is a quadrilateral, so I know that it definitely, all 4 corners add up to 360 degrees. I've got 2 A's, I've got 2 B's, I've got 2 C's, and I've got 2 D's, and they all add up to 360 because it's a quadrilateral. If I half both sides, I end up with A plus B plus C plus D equals 180. A plus B plus C plus D equals 180. So I've proved it. Okay, obviously I would need to write some words down, but I'm trying to do this really quickly for you. Okay, the next one, let's do alternate segment theorem. So I need a triangle like that. Let's put the centre of the circle in there. Okay, so to prove alternate segment theorem, I'm trying to prove that this angle here is the same as that angle there. That's what I'm trying to prove. So what I'm actually going to do is draw a line, a radius from the centre to the tangent, like that. And the reason why that is helpful is because I know that radius meets tangent at 90 degrees. So I know that that there is 90 degrees. So I might use that in a minute. I'm also then going to join the radii to the other corners of the circle, like that. Not circle, triangle. So that I end up with 3 triangles. And I'm going to label all of these angles A, B, C, D, E, F, like that. You know what, I shouldn't have labelled them like that because these are isosceles triangles, right? So if that's B, then that's B as well. And that there's going to be A, because it's isosceles triangle. I know it's isosceles because they're radii. And then this is isosceles, so let's call that one D. Let's not worry about the fact that I don't have a letter C anywhere in my picture. Okay. Right, and because it's this is a triangle, all 3 corners have to add up to 180. So I know that 2 B's plus 2 D's plus 2 A's have to add up to 180. because angles in a triangle add up to 180. And if I halve both sides, I get that. So I know that A, let me colour it, I know that A plus D and B makes 90. So that means that A equals 90 minus B plus D. But I can also see from this picture that this pink angle, which I'm going to call X, is also 90 minus A, because the whole thing is 90, and if I take away A, I get that. So, you know what, I should have written this the other way around, shouldn't I? So if I say that A is, no, B plus D is 90 minus A, that's better. Then I can say, well, if X is 90 minus A, and B plus D is 90 minus A, then X must equal D plus B. And that has proven that this blue angle and this blue angle are the same, so I've proved the alternate segment theorem. Okay, next one. Angle at the centre is twice the angle at the circumference. Okay, so I start with something like that, and I'm going to cut it into two triangles, like that. Triangles are always useful in proofs because you know that angles in triangles add up to 180, so that can be really handy. I'm going to call this one A and this one B. This is isosceles because there's two radii, so I know that that's A as well, and I know that that's B. That's isosceles too. Okay, so then I know that this angle here is 180 minus 2A, because angles in a triangle add up to 180. And I know that this angle here is 180 minus 2B, because angles in a triangle add up to 180. So this angle here is going to be 360 take away these two added together, and if I work that out, I get 360 take away 180 is 180, and then I'm going to minus 2A, I'm going to minus 2B, so I get that. Oops, no I don't, there's two 180s, so actually that cancels out the 180, the 360 completely. So I end up with just 2A plus 2B, which is great because that is double of A plus B, and therefore it is proven. Okay, next let's do angles subtended from the same arc are equal, or as I call it, the angles in the same segment are equal. So that says that when you've got something like that and something like that, these two angles here are going to be equal. This is really easy to prove from the one that I just proved, because what you can do, and this is probably the worst diagram I could have drawn, to be honest. If I draw the angle at the centre like that, I know the angle at the centre here, I've just proven that the angle at the centre is double the angle at the circumference. So if that is x, then this angle here is 2x, because I already proved that. But equally, if this is 2x, then this is the angle at the circumference, so this must be half, so that must be x. So that proof, as long as you already know the angle at the centre is double the angle at the circumference, this one is kind of like obvious. Well, not obvious, but the proof is it just is all based on that. I don't think they're going to ask you this one because the proof is a little bit, I don't know, simple. I think that's all the proofs that you really need to know for circle theorems, I think. If they're going to ask you one of those, I think it'll be one of them. I think you're most likely to get cyclic quadrilateral or angle at centre and angle at circumference. I don't think they're going to ask the alternate segment theorem, but if they do, the key is to join up all the corners to the centre and get some isosceles triangles. Okay? I hope that was useful to you, and I hope you enjoy all the circle theorem questions that you get in paper 1 tomorrow. Bye!